Hello, welcome to lecture 10. In the previous lecture, we were discussing the Bose-Einstein approximation. We showed how the continuity equation changes to a form which is similar to the incompressibility condition, the Bose-Einstein approximation again imposes a restriction on the velocity field that it has to be divergence free. And we also saw how the momentum equation changes. We'll start from that momentum equation today. So the momentum equation, as you can see on the screen, is written in this form, and we have neglected the rotation term, the Coriolis acceleration, but that is does not really play a role in this Bose-Einstein approximation, and that is the reason why we have neglected. And what we show here is the momentum equation without rotation, and we said that the Bose-Einstein approximation, we throw away all the terms, all the density variation terms, if it's multiplied with any other term other than the gravity. So this is the term that we should always retain. So even though rho prime is small, but it is multiplied with a very high acceleration. So acceleration due to gravity is the strongest acceleration in the momentum equation. Nothing goes faster than this in this momentum equation that we have in this form. So hence this rho prime term is multiplied with the highest acceleration, hence this is being kept. This is the essence of the Bose-Einstein approximation. So now we have done the momentum equation. Now we'll see how the energy equation changes. So remember, we had derived all these equations earlier, and then we are now trying to find out some simplified versions so that our calculations are slightly easier. So we are trying to see what simplifications Bose-Einstein approximation can give us. So the energy equation we had written down as rho Cv, the total derivative of temperature plus pressure times the divergence of the velocity field is equal to kT times del square T. So we had mentioned during the derivation of the energy equation that we are not assuming whether something is compressible or incompressible. The medium can be anything. But Bose-Einstein approximation has given us a constraint that the divergence of the velocity field should be zero. So this means this term is zero. This is what we derived. I mean, we had derived that this is equivalent to del dot u, and by Bose-Einstein approximation this is equal to zero. So hence the energy equation simplifies to rho naught Cv ddt equal to kT del square T. This is the simplified form of the energy equation. This can also be written down as ddt is equal to kappa T del square T. So this is kappa, that the one on top is in the first equation is K. So this is this is the kinematic diffusivity of heat. So kappa T is the kinematic diffusivity of heat, which is same as the form of the salinity diffusion equation. If you recall, we had the salinity diffusion equation as kappa S del square S. So this is now the form of the energy equation has reduced to the same form as a diffusion equation for salt that we had derived. This is within the Bose-Einstein approximation. So Ks and Kt, kappa S and kappa T. So these are kappa S and kappa T give you respectively the diffusivities for salinity and temperature. And as I mentioned, diffusivities give you an approximate time scale in which something mixes with the ambient. So if you put some if you give some heat into a system, how much time does it take to diffuse in the system? If you add some salt into a system, how much time it takes to diffuse into the ambient. So these are all molecular processes that we are talking about. So these actually, the kappa s and kappa t are variable, that is they are different from each other, and kappa t is approximately 100 times. So the kappa t is approximately 100 times kappa s, approximately 100 times kappa s. So this gives rise to variable diffusion. So um, uh, if you have seawater which has both, it has both temperature and salinity, something is it has so temperature and salinity have their own diffusivities, which is given by k kappa s and kappa t, and they diffuse differently. So in small scale systems, in meter scales, so this gives rise to variable diffusion, and this gives rise to double diffusive fingers. So because they are variable, so this gives rise to phenomena called double diffusion, and one of the representative features of this are salt fingers. So there are finger-like protrusions of salt that can that are seen. This is a very rough diagram. Cartoon that I'm making. So there are very small scale salt fingers that you will see because of this variation, this difference in the diffusivities of temperature and salinity, and this happens with an approximately in a scale of approximately a meter. Because if you go for larger scales, turbulent processes can change the diffusivities, and it of course does. It increases by significant magnitude. These scales, these small scale features are not seen. So in order of few meters, in order of meters, we'll see those. We can see these salt fingers, because in those scales, molecular diffusion is um, prevalent. Whereas in large scale motions, it's mostly turbulent convection, turbulence driven motion, and we'll get to turbulence later on. But this is just something that you can keep in mind. These are all molecular values. So these are all molecular values. So for double diffusive convection, so there's a suggestion for a book that you can follow. So J.S. Turner has a book which is called Buoyancy Effects in Fluids. It's a book that can be followed for someone who is interested in pursuing this further. So now in these equations, we only have the total pressure and the total density do not appear. So we'll drop the primes from here onwards. So these are only perturbation pressure and perturbation density. We have here in this momentum equation only rho prime and p prime appear. The absolute density and absolute pressure do not appear. So we'll drop the primes, and we will take it. We'll always assume those p and rho to be fluctuations over a mean value. Okay, so hence the final set of Boussinesq equation. So the final set of Boussinesq equation looks something like this. Del dot u equal to 0. This is the conservation of mass. Del u del t is equal to minus 1 by rho naught. Sorry, I'm trying to write this in component form. So I'm writing individually all the three momentum equations. So these are the x and the y momentum equations. The z momentum equation is the one where we don't throw away the density variation when it is multiplied with the gravity term, dw dt equal to minus 1 by rho naught del p del z minus rho g by rho naught plus nu del square w. Remember that p and w are in all of these equations, p and rho are the fluctuations over a mean. So and then the energy equation, it is del t ddt equal to kappa del square t. So this is the final set of equation. So we have the continuity equation and the momentum equations and the temperature and the energy equation. Now this term is important. We have retained this term, and because we have retained this term, it's we name it because it's an important term that will keep appearing as we go along. The term minus rho g by rho naught is called buoyancy. Okay. This is represented by the alphabet B, the symbol B. So remember then that in these equations, this rho is actually rho prime. So we had agreed to throw away the primes for simplicity, for the sake of understanding and for writing it simply. So in all of these, rho is actually rho prime, that is, it is the fluctuation density. So from this, we can say that when rho is less than 0, so it's fluctuation, so it can be less than 0, the parcel of fluid which is liquid or gas is lighter than the ambient. That is, B is greater than 0 in this case. Okay, so buoyancy is it has a positive buoyancy. I mean, we might have heard speaking in our common language that it's a buoyant system, it's a buoyant fluid. That is, it has an upward acceleration and it has a positive buoyancy, so it denotes upward acceleration. However, when rho is greater than 0, because there is a negative term in front of this buoyancy, if rho is greater than 0, B is less than 0. So this means there's a downward acceleration. So this is this happens when the parcel of fluid is so the parcel of fluid is heavier than the ambient. Okay, so this gives us a downward acceleration. Hence, buoyancy is a measure of how light or how heavy a parcel is as compared to its ambient. So the Boussinesq equations are important because we'll be using it while we are looking at while we discuss wave propagations later in this course, because waves cannot exist unless there is there's a density difference, and the density differences, and once we have density differences, we will need to use the Boussinesq equations. So these equations are also used in stratified turbulence, but we will only touch on that stratified turbulence topic in this course. We will not go deep into the detail. So the Boussinesq approximations are valid. So So these are valid only when density differences are small. Density differences not very large. Are not very large, and the Mach number is small. The flow speeds are less. Small Mach number, density differences are not very large. So that means if your system has very high temperature gradient, very high salinity gradient, your Boussinesq approximation will not be valid, and you'll have to use the full momentum equations and not the reduced form that is given by the Boussinesq approximation. So now once we have completed the Boussinesq approximation, we do a related approximation. So this is called the N-elastic approximation. So you will see that Boussinesq approximation is a subset of this N-elastic approximation. So N-elastic approximation can be applied to motions even when the vertical variations are large enough. So we said that the density rho naught, which is the reference density, does not change, and hence the continuity equation just has the form del dot u equal to 0. Whereas there are certain atmospheric phenomena which can be of order of 10 kilometers. For example, a deep circulation goes up to the height of the tropopause. So in this case, the background temperature varies, and the background density, which is the atmospheric air, changes because of a very big change in the hydrostatic pressure. So the background density for large scale motions, for deep convection, large scale motions, so this is, let's say, of order 10 kilometers, the background density is a function of z. Background density is a function of z. The density is not a constant. If you recall, while deriving the conservation of mass equation, we have said that the density is constant, the density rho naught is constant, whereas for deep convection, the background density itself can change. For an atmosphere, the change in density is approximately 3 to 4 times, but it all depends on the time of the day or the moisture content in the atmosphere. So hence, from the continuity equation, we have del dot rho naught u equal to 0. Remember, we had thrown away the rho naught term, but now we are keeping the rho naught term. So this is the continuity equation under the N-elastic approximation. So this is the continuity equation with the N-elastic approximation. Del dot rho naught u equal to 0. This means the Boussinesq approximation is a special case of N-elastic approximation. If your background density is varying with the vertical coordinate, in this case we are taking vertical coordinate. Of course, it can vary with horizontally also, but to make our calculation simpler, we are assuming that the reference density itself is varying with the coordinate z, which is the vertical coordinate. If that is the case, we need to take the total continuity equation to be something like the divergence of the rho naught times u to be equal to 0. And the Boussinesq approximation, as you can see, is a special case where we take rho naught equal to constant, and in this Boussinesq approximation the continuity equation just becomes del dot u equal to 0. So hence Boussinesq is a special case of the inelastic approximation. So now, as I mentioned during the derivation of the governing equation, that we will be discussing some topics of interest, which are related to the governing equations, which dictate the motion of the fluid, but not, it's not directly derived from the governing equations. So one of the other, and hence we said, we discussed the Boussinesq approximation in that sense. We said that there is an approximation which helps us simplify the equations. So we are not getting deeper into the equations per se, but we are just trying to simplify the equations. We are not trying to solve the equations. We are not talking about the boundary conditions yet, but we are trying to simplify the equations so that our numerical solutions become slightly easier. So we derive the Boussinesq approximation. Now there's a related topic which is something that we must understand once we have understanding of our governing equations. So let's discuss something called stratification. So the reason why we're discussing this is because we have already discussed the effect of rotation in the previous lectures while we're deriving the governing equations. And if you recall, in the first a few lectures we have emphasized really hard that geophysical fluid dynamics are affected by stratification and rotation. So we saw how the momentum equations are derived, momentum equations change due to the presence of rotation, because we are measuring from a rotating frame of reference. We also need to understand stratification first of all. This will not change the momentum equation directly, but this is necessary because we need to understand that the density that we are taking can also change with one of the directions. It can either change in vertical direction or in one of the horizontal directions. So this is, again, we are not going to derive directly or change the momentum equations significantly similar to how we did with the Boussinesq approximation, but this understanding of this term will give us an idea of how the equations of how we can perceive the equations of motion, or what kind of motion we can expect these equations to admit. So these we'll see that presence of these density changes will give rise to something called waves. We'll get to waves later, but we'll see that this gives rise to wavy motions. And that is the reason why we need to understand the effect of stratification also. So this is directly comparing with the rotation part that we had done a few classes earlier. So now we are studying the effect of stratification. So these two, stratification and rotation, are very important for geophysical flows. So stratification is variation of property variation of a property with change in position, with location or position. We will use a simple system where the property varies only with the vertical coordinate. So in our studies, in the cases that we will consider, so when you say stratified, so we will say either it is stratified in temperature, it is stratified in salinity, or both, which gives rise to stratification in density. So temperature can vary, salinity can vary, or both can vary, and this will directly lead to changes in density. We saw that the equation of state gives us a linear relationship between density and temperature and salinity. So if temperature and salinity are varying, density can vary. So we are considering only vertical variations. This is to make things tractable. You can include other variations also, but this is just to have a first understanding of what stratification actually brings into the brings to the table. So only vertical variations we'll consider. So to consider this, let's have a system of we consider a system which is in static equilibrium. So we consider a system where density is varying, density is increasing with depth. So this is density, and this is the coordinate z going upwards, and this density has a profile which looks something like this. So it is heavier so the system is heavier below and lighter on the top. Okay, z is the coordinate, and let's say we have a fluid, so we have an element which is at location here, which is at location z, rho z, and this is being taken up to a position which is separated by a distance h. So we are taking a parcel of fluid, water, liquid water or air, from one height to another height, z plus h. Okay, so distance is h and the density is heavier at the bottom. So that means rho z is greater than rho z plus h. So once we do this, so for an incompressible fluid, the changes, the parcel will retain its density even though there is a change in the hydrostatic pressure. Even if we take parcel from this position, let's call it position 1, let's call it, so let's call it position 1, let's call it position 2. So taking it from 1 to 2, and the parcel of fluid will retain its density. It's an incompressible fluid. So as it is in an environment, as a lighter environment now, so rho z plus h is less than rho z. It's a lighter environment. It experiences downward force, which is equal to a downward force which is equal to gravity times the density change and the times the volume. This Archimedes principle. So this V is the volume of the parcel. So this is the volume of the parcel of fluid. Now this is the downward force using Newton's law. Newton's law we can write as rho z v d square h dt squared. This is the total acceleration of the fluid. This is equal to the force which this is experiencing. Okay, the acceleration of the fluid is equal to the total, mass times acceleration is equal to the total external force which is acting on the parcel. So as the density variations are weak, so we replace rho z by rho naught. We assume that the density remains constant in the I mean, we can change the variation. I mean, we can replace the variation of density with Z to be just a reference value, rho naught. And on the from the right hand side, rho Z plus H minus rho Z is approximately equal to d rho by dz times H. So we do a Taylor series expansion because the density variations are weak. So equation 1 reduces to del square H by dt square equal to G by rho naught d rho by dz times H. This gives del square H by dt squared minus G by rho d rho by dz times H equal to 0. Okay, so this if we have from this d rho by dz less than 0, that is higher density below, this is the situation that we start with, then minus G by rho, so here it is rho naught, so minus G by rho naught d rho by dz is greater than 0. Okay, so d rho by dz comes into, I mean, there's a negative sign in front of it since this is greater than 0. So we define something, we define the quantity, I mean a variable n squared as minus G by rho naught d rho by dz. This is a quantity that we are defining. Hence the equation of motion, I mean this simplifies to d squared H by dt squared plus n squared H equal to 0. So this is an oscillatory motion if n squared is positive. Many of you, I think all of you will recall the simple harmonic motion. So this is if n squared is positive, the solution is an oscillatory motion. So solution is an oscillatory motion. So what happens, I mean, why is it an oscillatory motion? So if you are taking a fluid parcel from its position to location z plus h, and you leave it, it is heavier, it falls down, it attains a vertical velocity, it goes back, I mean goes further down up to a certain depth, and it finds itself now in a situation where it's more heavy, it's lighter, so it's going from position 1 to position 2, and it falls down up to a certain location, position 3, where it finds itself to be lighter, and it goes up again up to a certain position 4, and it again goes down because it finds itself to be heavier here, goes back to position 5. So it does an oscillatory motion, goes up, comes down, goes up, comes down, goes up, comes down. So it does an oscillatory motion. So the solution is an oscillatory motion. So this this quantity n squared that we have defined is called this quantity n squared is called the stratification frequency, or it is more commonly called the Brunt Weissala frequency. Is more commonly called the Brunt-Weissala frequency, named after two scientists, David Brunt and Wilhelm Weissala. So this is the frequency by which this oscillation happens. Sorry, this n is called the stratification frequency. N, sorry, this is not n squared. N is called the stratification frequency. So the earlier equation looks similar to d square x by dt squared plus omega squared x, where omega is the oscillation frequency. Similarly, we have written down n to be the stratification frequency, or this is the Brunt-Väisälä frequency, or the frequency of oscillation of this fluid if you displace it in a stable stratified medium.